Kia ora koutou katoa, it's Mrs. Goodson here. This video is about energy changes for level 2 chemistry, bonding and structure. And it's about how to identify and describe exothermic and endothermic reactions. Chemical reactions involve the breaking and making or formation of chemical bonds. The general rule is that energy is absorbed from the surroundings in the breaking of chemical bonds, and energy is released to the surroundings when bonds are formed. There are two types of energy changes when a chemical reaction happens. In an exothermic reaction, heat is released to the surroundings from the system in the form of heat. So it releases energy. An endothermic reaction is when the system absorbs energy from its surroundings in the form of heat. So the heat is going from the surroundings to the system. Exothermic reactions release energy into the environment or into the surroundings. They feel warm or hot or may even be explosive. More energy is released making chemical bonds than is used breaking them. In an exothermic reaction, the enthalpy change has a negative value. That means the change in enthalpy is less than zero. Here are some examples of exothermic reactions. So the combustion or the burning of fuels, and heat and light energy are released. What about the reaction of sodium metal and water? And you get heat, light, and sound. When hydrogen and oxygen gases react, it's a almost explosive reaction, provides heat, light, and sound to the surroundings. Respiration is an example of an exothermic reaction, and it's like controlled combustion, but reaction of glucose with oxygen. And energy is released as ATP, which is a form of energy that cells can use. Endothermic reactions are reactions that absorb thermal energy or heat from its surroundings. Because heat is absorbed, endothermic reactions feel cold. The heat absorbed by the reaction provides the activation energy needed for the reaction to occur. More energy is needed to break chemical bonds than is released reforming them to make new products. So this means that the energy enthalpy change in an endothermic reaction is positive, or change in H is greater than zero. So more about exothermic reactions. A chemical reaction that releases heat and has a negative standard enthalpy change. So water and acid reaction, a fire, rusting, nuclear fission, that's a big explosive reaction, freezing water into ice. So heat energy is produced by the reaction and the temperature of the surroundings increases. For example, sodium hydroxide pellets and water. The water gets warm, therefore dissolved. Sodium hydroxide contains less energy than solid sodium hydroxide. So the energy gets released. This is more about endothermic reactions. These are the ones that absorb heat from the surroundings and feel cold. Photosynthesis absorbs energy from the sun. This reaction is showing the heat going from the surroundings into the solution, dissolving salt and water. So heat energy is absorbed, temperature of the surroundings decreases. For example, dissolving solid ammonium nitrate, the water becomes colder as ammonium nitrate absorbed energy from the water. Dissolved ammonium nitrate has more energy than solid ammonium nitrate. So, how do we recognize exothermic and endothermic reactions? So, this slide compares them. So, exothermic, the test tube gets hotter, the temperature increases, energy is a product Products have less energy than reactants, so therefore change in H is negative. Compared with endothermic reactions where the test tube gets colder, the temperature of the reaction decreases. Energy is a reactant. Products have more energy than the reactants, and so therefore the change in H is positive, or the change in enthalpy. So we can show this on an energy level diagram. And these show how much energy the reactants have and whether or not the products have more or less energy than the reactants. So in an exothermic reaction, the reactants here have more energy than the products here. So the difference is the energy released. This compares with the endothermic reaction, where the reactants have less energy than the products, so the difference is the energy absorbed. If a reaction is endothermic in one direction, it will be exothermic in the other direction. So A plus B equals C plus D is if that's exothermic, then the reverse reaction will be endothermic. Substances have an amount of energy, either kinetic or potential. So this is already explaining a bit more about what enthalpy is. Enthalpy is the heat content of that substance. We can't measure all of the heat, but we can measure the change in heat or the change in enthalpy. So we always talk about delta, or that's that triangle, delta H, which is the enthalpy change. This is also called the heat of the reaction, and sometimes there's a little R there for heat of reaction. And the unit for that is kilojoules, a little k and a big J, kilojoules. And you'll see that on packets of food, for example, that's the amount of energy in the food when your body uses it. Okay, energy change is the difference between the enthalpy of the products and the enthalpy of the reactants. So the enthalpy change, or the delta H, or heat of reaction, is the heat in the products minus the heat in the reactants. So the change in enthalpy is negative or less than zero in enthalpy and exothermic reactions. So this is when the reactants is, so this is when it's, so we see a negative here, look, in this example. If you see a negative sign here, then it's exothermic. Compared with an endothermic reaction, the enthalpy is positive, change in enthalpy is positive or greater than zero, and the products have more energy than reactants. So we're looking for a positive value here in the thermochemical equation. This value here, if you see a positive here, then it's endothermic. Enthalpy change is dependent on making and breaking bonds. Bond making or bond forming is exothermic. Energy is released. Bond breaking is endothermic. Energy is absorbed. So if the overall reaction is exothermic, more energy is given out as the bonds of the products form than is taken in as the bonds of the reactants break. If overall is endothermic, then it's the vice versa. To break intermolecular bonds requires energy. For example, going from a solid to a liquid or a liquid to a gas, it has to absorb energy from the surroundings. Now, I just included these graphs to show that sometimes you see the graphs with this little bit here, which is the activation energy. This is a little bit of energy or a lot of energy needed to start the reaction. And in an endothermic reaction, it's that much there. Is that the whole thing there is how much energy is needed to start the reaction. So that's but again, the reactants are lower energy than the products. That's the main thing. And so the change in enthalpy is positive. Here are some examples. Dehydrating blue copper sulfate crystals to form anhydrous copper sulfate. It requires input of energy, so it's endothermic. Melting ice is endothermic because it gains energy before it melts. Reaction of calcium with water, that gives off heat, so it's exothermic. and formation of snow from water vapor. So that is going to a solid from a liquid. So the snow is lower energy. So going from water vapor, the gas, to the solid is exothermic. This video has been about identifying exothermic and endothermic reactions from changes in temperature of the surrounding environment, and identifying and being able to draw energy diagrams for both exothermic and endothermic reactions.